We're starting our study of equilibrium. That's the singular. Equilibria is the plural. And you need to have your exit ticket 17.3 ready for this presentation. So we know that some reactions are reversible. We've hit this several times, and especially we hit it in Hess's law. So you know reactions are reversible. Not all, like rusting is not, but certain things like the oxygen attaching to the hemoglobin in your blood is reversible, which is a good thing. Chemical reactions that can go to products or reactants depending on the conditions. So we're going to talk about favoring the products, which will be the forward reaction, that's favoring the right side, or we're going to talk about the reverse reaction where we favor the reactants and the arrow pointing to the left is dominating. So here's an example, SO2 and H2O making H2SO3. This is a gas combining with rainwater to make acid rain. This is reversible. Look at the double arrows. A dynamic equilibrium of this system would be one in which the point at which the rate of the forward reaction equals the rate of the reverse reaction. We're not saying the concentrations will be the same on the both sides. We're just saying at some point you start your forward reaction and then sometimes some reverse reactions start happening. And when you hit the conditions where the rate going forward and making the H2SO3 equals the rate of decomposition of the H2SO3 into the SO2 and H2O, that's called equilibrium. It's about equal rates, and that's the only thing that's equal in equilibrium. The number of molecules changing to products then will equal the number changing back to reactants. So the rates of change are the same. It doesn't mean the concentrations will be equal. As a matter of fact, they definitely will not be, and we're going to use those concentrations of equilibrium conditions to calculate something called an equilibrium constant. The state at which concentrations of products and the concentration of reactants remaining the same for those conditions is called chemical equilibrium. So we're not saying the concentrations are all the same, but we're saying for a given molecule, its concentration will be stabilized at equilibrium conditions. Some of it will be changing back to reactants, but some of it from the reactants will be changing back to products, so the concentrations reach a stability level. The law of chemical equilibrium states every reversible reaction proceeds to an equilibrium state that can be described by an equilibrium constant at a specific temperature. The only thing that messes up your equilibrium constant is changing the temperature. We'll get to that more later. Equilibrium means balanced, and in this case it's the rates that are balanced. The equilibrium constant is a measure of the extent of a reaction, the extent that it goes to completion, the extent that the products are favored. A really big equilibrium constant means we're favoring the products. So, for the equilibrium expression, that is going to be the mathematical way we deal with equilibrium. For a particular reaction where you have A moles of A compound plus B moles of B compound reacts reversibly with C moles of C compound plus D moles of D compound. These coefficients have always been important. They become extra powerfully important now because the equilibrium constant expression, or the formula we set up to do this math, takes the concentration, that's what those brackets means, the concentration of a product C raised to C power times the product D raised to D power. Those coefficients now become power functions. We're going to divide that by the reactants. The things on the left side go in the bottom. The concentration in moles per liter of A raised to the A power, that's the coefficient, times the concentration in moles per liter of B raised to the B power. So you really want to get this all down correctly. You should probably write this on the top of page 6 in your homework packet, because this is going to be the concentration formula that you want to use for all of the mathematics on page 6. Remember, the brackets means concentration in molarity, molar, moles per liter, capital M. Again, get this written down somewhere because you're not going to see it in the rest of the presentation. So the meaning of the equilibrium constant value, if it's really big, greater than 1, significantly greater than 1, and we can't put a true value on that, but if it was like 800, then we know that more product will be produced than reactant. The forward reaction is favored. Equilibrium lies to the right of the written equation. If the equilibrium constant is much less than 1, it's significantly less than 1, then we know that the reverse reaction is favored. Equilibrium lies to the left is the way we're going to say that. The reaction doesn't really start going. So the reactants will stay present and they don't turn into products. So tiny equilibrium constants mean the reverse reaction is favored. Equilibrium of 1, if it's exactly 1 or just about 1, it means you'll end up with equal amounts of reactants and products. We have the word homogeneous and heterogeneous again. Homogeneous is the same. That means the whole reaction is in one state of matter, either all aqueous or all gaseous. And the heterogeneous equilibrium means the reaction has more than one state of matter and includes solids or liquids. This is a big hint. The equilibrium equation that we've used uses only gases and aqueous solutions. The amounts of solids, S, and liquids, L, don't measurably change at equilibrium. Their concentrations stay pretty stable. They don't change. So they're never put into that equilibrium expression, the formula that we wrote for calculating KEQ. So there's no place in the notes for you to write that. You might just want to make a note of it. So here's some sample problems. It says write the equilibrium expressions for the following reactions. I've given you the equilibrium expression formula again, just as a reminder as we get this started. So we're given 4 different equations. If I were you, I would pause the video right now, try to write them in the form of KEQ. Pause the movie, and you can turn it back on when you've done all these, because I'm about to give you the correct answers. Here we go. There's your correct answers. Over here on the right side, I've shown you. We take the NH3 raised to the square power because it's got 2. So that becomes this 2. And these are the products over the reactants concentrations, and because the hydrogen has a 3 for a coefficient, it becomes the 3 power function. Again, in the next one, we've got products over reactants with each coefficient becoming a power function. Check your other work on these other 2. You can pause the slide here and then move on. I'm moving on. Calculations with KEQ. There's 3 examples. I'm going to go through a couple of them for you. The first one, calculate the value of KEQ. If the nitrogen concentration is 1 molar, the hydrogen concentration is 2 molar, and the NH3 is 3 molar. So the first thing we want to do is write the equilibrium expression given for this given equation, and it's going to be NH3 squared over N2's concentration times H2's concentration cubed. So this first one, we just plug in the numbers. For NH3, we're using 3 molar, and we square it over the concentration for N2, which is 1 molar. We don't have to do anything to that. And the H2's concentration is 2 molar, and we need to cube that, and you solve it, do that math, and you should get 1.125. That's your K equilibrium. There's no unit on this number because the molarity units all cancel. So let's move on to the next one. Here's another example using the same equilibrium expression we used in the previous problem. We're going to say now we're given KEQ. So KEQ is 25 equals the concentration of the product. So that's going to be 4 molar, and we square that one, over X is what we're solving for, times the 2 molarity of the second reactant cubed. You solve that, and you find out that X equals, or the concentration of NH3 concentration equals 0.08 molar. Okay, next problem. We are given the KEQ, 0.0055 equals the concentration of products. It's the NH3. We're going to figure that one out. and we know it's x squared, concentration squared. The concentration is squared. Over the concentration of the N2, which is 3 molar, times the concentration of the H2, which is 2 molar, and we have to cube that. That'll equal, once you do it, you're going to get that x squared equals 0.132. You take the square root of 0.132, and that equals 0.3633 molar. That's your concentration of NH3.